So I will go ahead and do a this is the point we'll edit to opening now that I see that we have a bunch of you out there. So thank you. Hello and welcome to Learning Space, a production of CosmoQuest out of Southern Illinois University, Edwardsville. I am Dr. Pamela Gay and I am one of your hosts for the evening. Joining me this evening is my colleague, Georgia Bracey. I am at home. She's still on campus so that we aren't both taxing the same wireless router. It's true. It's true.
It is true. It's much better for me here.
So thank you so much. And I'm so sorry that this was such a last minute failure to warn people ahead of time. It has been a crazy 2 months around here. December kind of was one of those months where we knew we should be getting a NASA grant, and we had paperwork and we had processing, and I had conferences to go to and end of semester and stuff and things and holidays, and we survived it. And as we moved into January, along with conferences, a kickoff meeting. We are getting a large NASA grant. We got the official award letter yesterday. There will be press releases next week. So that's all I'm going to say. Although if any of you are watching Astronomy Cast, we got the award letter during the live recording of Astronomy Cast. So I squeaked a little bit. So I did want to say thank you for coming along for the ride, but the ride's not over. While we are getting significant NASA funding to work on citizen science and educational products, all of the work that we do through media, 365 Days of Astronomy, Astronomy Cast, this Learning Space Hangout, none of this is paid for. It's actually something that we're not allowed to spend our NASA funding on. So it is thanks to those of you who are sponsoring us through Patreon that we're able to do this. And right now, now that I've actually read our Patreon page correctly, we are getting wonderful sponsorships that allow us the time to do one show a month. We do have to do this on paid time just because of university rules, things and stuff. So we're deeply grateful for all you've done to allow us to keep doing this. And no one at the upper level of CosmoQuest, except for our beloved programmer Corey, is actually fully funded to do just one thing. All the rest of us are spread across like a dozen different projects. And Learning Space is part of what allows us to get full-time salaries. So because of you, Georgia and I both have full-time jobs, and we're very, very grateful for that. So as thanks, one of the things that we have as a thank you for donating is fireside chats, and I'm going to start doing those every Wednesday. I'm going to be I'm going to be Patreoning out to people after the show is over to set up who wants to just sit on the internet and talk about science things and stuff. So we're going to work on getting that going starting next Wednesday. But for today, we have some kind of awesome science that was inspired by an image by Louis Argerich, I think that's how you say his name, that flew across my Twitter feed. And I'm going to share this image with you.
I haven't actually seen this image.
Okay.
Now that I've heard you talk about the image.
Yeah, I keep talking about this because it is such an awesome image.
I have not seen the image. Okay.
So in this image, this streak that you see cutting across the screen in a diagonal, and if I get the whole image in the clip, you can actually see it goes from yellow to this is more bluish. That is probably a meteorite that had different ionization energies as it passed through the atmosphere, and apparently exploded a couple of different times and gave off these wonderful flashes of color. Now, at the same time, in the same image, we have a comet, and then we also have in the background the beehive cluster. So all of this is documented down here. This is Comet C 2013 R1 Lovejoy, and the beehive cluster M44, and just an interrupting meteor, because that's what meteors do. And what I loved about this image, and what was pointed out as it came through my Twitter feed, was The comet glows in reflected starlight in this image. So this is light from the sun that has traveled out past the Earth and, or at least out where it's on the nighttime side of the Earth, reflected off of the comet and then traveled back to us. All of these stars in the Beehive cluster, these are all hot objects happily radiating away a black body continuum of light. And this light that we see here is created by the energy, the heat, the kinetic energy of the meteor ionizing the atmosphere around it and giving off this light. So this show is thanks to this image, thanks to Louis Argerich, and you should all check out his work on Flickr because it's really kind of amazing. So while I have been just quite happily staring at astrophotography, George has been out pulling together actual educational materials and can take this thing that inspired me and sort of got me going, light is awesome, and turn it into an educational context.
And so your idea is when it's interesting to me, you look at that picture and you get all of that good stuff out of that picture because of your expertise in physics and astronomy. You look at light and you look at those pictures in quite a different way than like a very young student might. And so part of the fun and the challenge is to think about how a young student would look at that picture and what they would see, and they certainly wouldn't get as much out of it as you would, but they would get some pretty cool things out of it. They would see different shiny things there. And that picture, certainly could spark a lot of great conversations in the classroom. And so you could start to talk about light and all the different things that light does. And things that, although this was such a cool moment for you, a lot of us just sort of take for granted as we're, just walking around being adults in this world, is we have light, things shine, things blink, they do their thing, and we don't really think about exactly what's going on. So it's very cool that you looked at that and saw all these different processes going on. And so you can start to bring things like that out in your students' mind as well, but you need to start simple.
Now, at what age do little childlings start to piece together the fact that the reason we can see each other is somebody turned on a light and the photons, the light coming out of the light, is reflecting off of us?
Yeah, that's actually one. So that's a great point. Ideally, if you're a teacher and you have a really sort of coherent, cohesive curriculum, you start at these very simple yet fundamental ideas. How do we see? Why do we see? And then you build as you go up in grade level and up the curriculum, and those are called learning progressions. And those are things that lots of education researchers are trying to develop for all the big ideas in science, all the different disciplines. Energy is a big one. What do little kids need to know to start out to someday, arrive in high school and be able to understand the more complex ideas? So going back, little kids should be able to understand that we need to have light shining on things in order to see. And so, again, something really simple. I pulled, there's a couple of things we'll put on our blog post in Educator Zone that we'll talk about in a little bit, some learning, some lessons, but I pulled one lesson and got some really simple things you could do. And one, honestly, is just to either turn off the lights or teachers, you have to know your students. You maybe just tell them to imagine that the classroom is completely dark, because chaos can ensue if you try to get all of your kids in a really dark place. And ask them, to think about that, imagine that, and then, what would it be like? And so elicit the ideas that, well, we wouldn't be able to see anything. We might run into things, we might knock things over. And so what would we need then to see? And so we would need a light of some sort. So you can get the idea from them that, light comes from a source somehow, and we need that to see. And that's the first basic kind of thing kind of idea to talk about with kids. And it's something they don't usually think about. You have to bring that out. So, and then you can build on it from there. So what happens when, light gets to an object? There's a source, but then light hits that. And is that all there is? Well, no, our eyes are involved, and the light has to get from a source to an object to our eyes. And so you can begin to develop all of those ideas, one on top of another. But start very basic and have the kids tell you what they think, because it's really important to get their ideas out, because they have some amazing ideas, but they also have some really off-track ideas that you need to talk about with them and provide them with some activities so that they can kind of run up against their ideas that don't maybe quite make so much sense, and kind of be guided back to, a more scientific description of what light is and how we see things.
Now, have you seen it? It isn't The Private Universe, but one of Phil Sadler's other videos. He put some kids one at a time into a light-proof room, turned off the lights, absolute darkness, and he asked one how long he thought it would take, or it was a carefully worded question, not a leading question, which is about to come out of my mouth. He asked them a question about dark adaptation, and these kids thought that if you stayed in this perfectly dark room with no sources of light long enough, eventually your eyes would still dark adapt to be able to see in this absolute darkness. How do you overcome these kinds of ideas about the absence of light?
It's, the conversations, and if you can come up with some examples that relate to experiences that, even if all the kids haven't had them, but maybe some of them had, sitting in a dark closet. But even sometimes that's not enough, because little bits of light do get in, and what kids imagine as pure darkness is hardly ever, pure darkness. And so that's difficult, because we don't, you think about it, we hardly ever experience real pure darkness. Maybe some of them have traveled and gone on vacation and gone in a cave, and
Yeah.
you always get to the fun part of the cave tour where everybody sits down, and then the ranger will turn off lights and ask everybody to please put their cell phones away. And for a minute you sit there and you truly can't see your hand in front of your face, and you sit there and it's still dark. But that really is an unusual experience. And so that's what that's the tough part of any kind of teaching, is to sometimes realize you have to overwrite all of these years of subtle experiences where for years we've never experienced true dark. So what we think of as dark, we go to bed, we turn out the light, we can't see a thing for just a few minutes, but then gradually, oh yeah, now I can see. So it's perfectly reasonable to have that misconception, or that naive conception. And activities, really good conversations with students is one of the ways, probably some of the only ways, to really get at that. And there's really no magic, instantaneous procedure that's gonna erase all of that experience. So it takes some time, and it's not easy.
So that first struggle is clearly getting kids to understand there's light and there's no light, and in order to see things around us here on Earth, we're either looking at light bulbs, which are emitting light, or we're looking at reflected light that's either reflected from those light bulbs or from the sun. And what's kind of cool that wasn't true when we were kids is nowadays the light bulbs around us are generally interesting if you're able to spread their light out into a spectrum. And I know you have one of the little diffraction gratings there on your desk that you can get.
I have a couple of cool things.
Yeah.
Light is fun because there's lots of just easy activities you can do just to let kids explore and discover things. So you can get very cheaply, this is a little diffraction grating, and like a little slide.
Can you actually put that in front of your camera, and then do you have a flashlight maybe?
It seems
So
like,
I
all
can
right, so
see
can you
some
see
little
some rainbows?
rainbows.
Okay.
Yeah. I think if you turned on a light, we'd actually be able to see
Oh,
spectrum with
all right, do you
that.
see? Oh, how
Yeah.
about that? Okay, very, ooh, that is cool. Seems like Nicole and I did something like this way back. So you can see, yes, the spectrum. So one of the next things you can talk about is, we normally see light bulbs and things, and they basically look white. Sometimes we have colored lights, but students can usually see that, oh, it's colored glass, or it's a colored piece of plastic that's in front of the white light bulb. So the idea you can next talk about is light white? Is white even a color? Is that all there is to light? And so it's very cool when you do one of these little diffraction gratings, or you put on the cool funky glasses that do the same thing, and the kids love to wear these around. And so as you look at the different lights in the classroom, you can see the spectrum. And, that is just, hours of amazement right there. So you can talk about, the light actually being made up of many colors. And then, of course, rainbows, they should be very familiar with that. Maybe not, how they're formed, but that's something you can connect to, and then they can look at or look out for, in the world around them. So that is, a next thing you can do with the kids, just to get them to think about what is inside light, in a sense.
Now, what's cool is, so the light that we deal with incandescent lights, and some of you probably still have old incandescent light bulbs stashed around. The color of the incandescent light bulbs is actually related to their temperature. So if you put them on a dimmer switch, and I'm just going to sort of like fake that here, if you put them on a dimmer switch, you can turn the electricity up, and you probably won't get them to be that blue. But as you turn them up, you can go from about 6,000 degrees color, where the distribution of the colors coming off the light bulb is what's shown in this plot. And I'm going to say add curve. Now, if I shift the temperature, I can actually change where that peak color is. So as the temperature goes down, my green curve gets redder and redder with what I'd see with my eye. And when you first turn on incandescent lights, you may notice that they're a little bit redder as they warm up. That's a word we've all used, but probably haven't thought through. As they warm up, the light gets bluer and bluer, and our eyes, just because of the way the eyeball works, happens to perceive it as more and more white. Now, what I'm playing with here is a black body simulator from the Nebraska Applet Project. Our good friend Kevin Lee is one of the people that worked on this. And if you have a dimmer switch, you can move the temperature up and down and watch the color go up and down with it. Now, at the same time, nowadays, most light bulbs aren't incandescent. They're these fluorescent monstrosities that none of us know how to paint our walls or put on makeup anymore. And it's with these incandescent bulbs and the fluorescent bulbs that not with the incandescents, it's with these fluorescent bulbs and the compact sodiums that those little emission line gratings you have get really interesting.
And that's, I was reading something that's a way to show why they are more efficient than the incandescent, right? So the big thing is the incandescent bulbs, not very efficient, not good with saving energy, but the fluorescent ones are.
Yeah.
And I think you can see maybe even in that simulation, an incandescent, some of the light is being radiated, at the visible wavelength, but a lot of it isn't. And in fact, a lot of it is just being lost as heat. And you can feel free to correct me if I'm not explaining
No, you have
this
it completely right. So
the right way, because I wouldn't. Well, I might be explaining this to fifth graders, but I never had to. So I just thought I'd seen that as an example on one of these simulations that was, you could use this to also to show, why, light bulbs, the old-fashioned kind, are not very efficient. They do give off the nice warm color of light that, like you said, we love. Personally, I really miss my incandescent bulbs, and I hoard them. But they also give off a lot in the infrared, which is really, wasted because we don't really need the heat. Although sometimes that can also come in handy.
Many observing runs. I have sat and kept my hands warm on my desk light.
Yeah.
Now, if you look at those fluorescent lights, I don't know if you have the capacity to do that, but you have that amazing spectral thing with you.
Okay,
I don't know if I don't know
how well this will. Okay, yeah, but so a lot of the cool stuff that I get out of so I'm at the STEM Center actually, and so is Pamela. Not literally right now, but she's at home. But I'm sitting here in my office at the STEM Center, and we have this awesome resource center, which is a part of the whole center, and it's full of stuff. Great sciencey stuff. And so if you want something as simple as a diffraction grating or some goofy diffraction glasses, or you want mirrors or flashlights, or something as a little more sophisticated like this vernier spectrum tube carousel. Very awesome. This is available from the Vernier company. We have a couple of them. They're a little costly. I mean, not
but
bad.
This is why the resource center
and
exists.
This is why we get them, and then we loan them out free for teachers or homeschoolers or scoutmasters, whoever is doing these kinds of activities doesn't want to buy their own, and they can borrow ours for free. So I brought this into my office just to kind of show what this does. Is this has different tubes that you can put in around this carousel, and each tube is a different element of gas. So there's nitrogen, there's helium, there's hydrogen, there's a few others. There's actually some mixtures. There's one I know that's just labeled air, and there's one that's labeled carbon dioxide. So there's activities and things you can do, but you can also just turn this on and have your. So again, I don't know if you really can.
Yeah. Now,
a little bit of color.
I'm going to be evil. Do you have the coordination to put the diffraction grating over your camera?
I'll be juggling next.
Yes, you got it. Okay.
Ooh, all right.
We're seeing it. You're looking at air. That's air.
It could be, or it just could be that we're not seeing this. So I had a real fight getting these tubes in.
Complete rainbow.
Yeah. I'm just going to kind of turn this around a little bit. Ooh, pretty. But the idea, of course, is to give the students the diffraction gratings and things and have them take a look at these different tubes and, be able to describe which is which gas is which because of the emission lines.
And the reason that I could get grouchy and go, that's air, is because it was a continual rainbow. If you look
so talk about, what else you would see if you had like hydrogen.
Go ahead and see if I can pull up a hydrogen spectrum. So if you had hydrogen in one of those bulbs, when you looked at it, you'd see the bulb would appear, for the most part, red, which is not the most exciting color in the world, but it's a color. But if you were then able to look at the emission line through a diffraction grating like the one George has been showing, the light that the bulk of it is coming off in the red, there's also a few other colors that is coming off in as well. So that hydrogen emission spectrum, what we'd see is this red line at 656 nanometers. This is the hydrogen bomber line that is very famous. It's the one that a lot of astrophotography filters is centered on. There's also a stripy bit in the green, which appears a lot fainter. More faint at 434, and even fainter yet over at 410. So these different colors that we end up seeing allow us to say what's in the tube. And since we didn't see this specific fingerprint when Georgia put up the happy little tube of gas, I was able to go, air, it's air, and be quite sad because I was hoping for a happy little emission spectrum, but that's not Georgia's fault. It's a science project for kids, and we simply landed on the boring answer first.
Sometimes that happens.
Yes.
That's okay, you keep going. So this is all about spectroscopy, would you say, right? And I mean, how astronomers might use some of these ideas?
So what's really cool about this? I'm going to switch to showing a different picture now. The picture that we have for the cover of this week's Hangout is this amazing Aurora picture from Rocky Geller, I believe. I have the name in the show notes correctly. And this picture, which I'm now sharing with everyone, it shows this beautiful red aurora borealis, a meteor streak, the Milky Way. So we have meteor streak, Milky Way, aurora in reds and greens, and I believe that this fuzzy blob right here is Comet Pan-STARRS. I know Comet Pan-STARRS is in this image somewhere. But what's cool looking at this is that green down along the horizon and that orangey red, that is excited oxygen atoms that are being excited by our own Earth's atmosphere interacting with the sun's excited particles that got flung our direction. And so every time a kid goes outside in a dark place at the right time and on the right place in the planet and sees an aurora, which not every kid's going to do, so you do need to pull up photos of this. But what you're seeing is a mission that allows us to see what atoms in our atmosphere are getting, well, annoyed by the sun. If you see bright blue, that bright blue is nitrogen. And so each color reflects a specific thing going on. And this is a very tangible example of what we're studying when we look at distant nebula, what we're studying when we look at a lot of different atmospheric phenomena, where the atmospheres we're talking about are the atmospheres of stars.
So that's very cool. And I kind of asked that because Richard Drum has a question, which I have to admit, as a teacher, I would be trying to answer this question. His question is, how do we teach spectroscopy and quantum mechanics to little ones such that their heads don't explode? And that is something it's very tempting. And as a teacher, you're going to have kids, someone's going to ask a question, Aurora, I saw one on PBS last night or something. I was watching the show, how does that work? And you want to explain because of course they're curious, and you can sort of get at a simple explanation. But again, back to the idea of these learning progressions and how certain concepts need to be there before they can really understand other concepts they truly do build. You have to think about it, how much do you need to know before you can wrap your head around spectroscopy?
And
just think of all that's, the concept of the atom, the energy transfer, all types of energy, friction, kinetic, everything that you just, talked about in a few sentences in like 2 minutes, you unpack all that and it's, it's huge. And for them to really understand it, sadly, is really hard. And certainly there's probably a few kids that can or could. But
and Georgia's pointing out why they don't let me near small children.
I know. But, but it's tempting. It's so tempting because it's, the kids want to know. They're curious. So, so tell them, is the basic stuff about Aurora and, and do these activities and tell them, we're building our ideas about things. And because some of it is just, so far ahead of where they are, it's going to be difficult. And I've even, I've fallen into where I want to explain something and I'll try to explain it as simply as I can. I think one example was, how the sun, how fusion works and how the sun shines basically. And this was 5th grade. And I kind of, walked through this sort of simple, I thought, as simple as I could make it. And, and the kids are like, yeah. But, they're not really understanding. And it's, so you just have to go back to, give them lots of opportunities to explore and simple things. And some of them, they'll just take it as far as they can and hopefully, and keep going.
So let's give some real quick rundown of straightforward things you can do, that most of which we've already brought up. So when you're talking about things give off a whole rainbow of light, you can have them look with that diffraction grating at a cool light bulb, at a hot light bulb with an incandescent bulb on a dimmer switch. You can have them then, when you're talking about reflected light, take that flashlight that you use on a cloudy, dark, moonless night and shine it on something. And if it's a reflective something, point out how these reflections are what allow you to see different things, to get that path of the light clear. Now, ionization is a really darn hard one to try and get across.
Yeah.
And the only way I know how to get this one across is to say it's when you excite an atom. And sometimes when something gets really excited, it just has to shout. So when you drop your keys, it shouts by making a noise when it hits the ground, and that's the kinetic energy becoming sound energy. Now, when you inject energy into a gas in like an open sign, it glows red because it's shouting, I have energetic atoms, and those energetic atoms just happen to be arranged in the open sign. And I speak in analogies, and
Yeah.
I have to remember to do this with small children, and I don't always, which again is why they don't let me near small children. But it all comes out to basically getting people to think about what they're seeing, and this is what you stressed so well earlier on, is the importance of dialogue.
Right, and things that we take for granted all the time, as adults, as scientists, kids and sometimes adults haven't really just thought about. I mean, for example, does light go in straight lines, or does it kind of just diffuse and swirl around everywhere? I mean, we are used to seeing, first of all, a lot of diagrams where we see light rays, and they're going in straight lines, and they might bounce off something, or be bent, but it's always this straight line. And so that's something that kids haven't really, they haven't had a real reason to think about that, and they haven't encountered those lovely diagrams yet if they're really little. So another just a very simple thing that you can do is poke holes in the same place in like 3 little cards. I'll just show this real quick here. So these are just little index cards. Take a hole punch so it's in the same place in each card, and you line them up, and you can actually, this is amazing, you can use a little binder clip, like this, and then it will actually sit like if my hand were the desk, it'll sit like this. So you can hold your cards up right in a row, and tell the kids, take a flashlight and just arrange your 3 cards so that light shines from the flashlight through all 3 holes. And so what do you have to do to make that happen? It's, again, seemingly just a goofy, simple thing, but the, maybe obvious answer is that the holes have to line up. And so here's the idea that basically, at a simple level, light basically is going in a straight line. And you can have them move the center one, put it off a little bit, and they can see that, oh, well, then light doesn't make it all the way to the 3rd card. It's blocked, it needs that hole. It can't, like, when it hits something, go around. So again, those basic ideas start to form by just playing with simple things, but also by having a teacher, a parent, a scoutmaster, somebody, talking with them about what they're seeing and asking them questions. That's really the key. That's what takes a simple activity like this, and an activity you could use easily with outreach, because it's so simple. But the leader, the adult, is the one that really brings out the goodness in the activity by the dialogue.
And we're going to write up all of this to help you figure out how to start these dialogues in your classroom, with your scout troop, or just with your own little one at home. And one of the things we're going to start doing this year, that we started doing last semester, and we're going to keep building on this idea, is we're putting out show notes on our blog, giving you lots of links out to resources that you can use. And what we're going to start adding to that is also research links. So we'll link out to Phil Sadler's video that talks about, or actually shows kids talking about, how they think that you'll just dark adapt if you sit in that dark room long enough, so that you can start to understand what is the research behind the reasons that we're saying all of these misconceptions are there, and even better, what's the research that helps us overcome all of these things that are so hard to learn. We're going to write up how you can get access to the simulation from the Nebraska athlete situation, and what that fabulous carousel of tubes that started with the boring tube, how you can get your own Vernier carousel of light tubes to work with.
You have to leave people wanting more.
That's
true. What I've been told.
It's true. It's true. So we have this month landed on the fourth Wednesday of the month. We are going to sit down next week and scope out the next semester of activities. And so stay tuned on Patreon, and we will let you know what we have planned. And thanks for coming on this wild ride with us. When we started this, it was the two of us and Nicole Gallucci, and then I got sucked into management, and then Nicole went off and got an awesome job in Manchester, New Hampshire, and I came back, and everything's still evolving. And what's kind of awesome is in the coming months we'll probably have more people joining us, and this show will continue to grow, and we're here because of you. So thank you for your support. Thank you for being our patrons on Patreon. Yeah. And you have any closing remarks for him, Georgia?
I just want to add too that it's so cool to see, that like main group of folks that are there to say hi to at the beginning of every show. Thank you guys, especially that you managed to come in and be with us every time, and and then bring others along. But it's really awesome to get everything set up and see, it's kind of not the friendly faces, but the friendly names, and,
friendly
and
avatars.
The comments. Yeah, exactly. So it means a whole lot. So yeah, thank you from me too.
And we will see you soon. And I will send out information on how to join me in a hangout just for you, or at least just for the patrons. So thank you very much. Have a great morning, afternoon, or evening, wherever you are in the world. And I believe our next event will be the Weekly Space Hangout on Friday, hosted by Fraser Kane at noon Pacific. And I hope to see you there. So have a great day.
Bye, everybody. Thanks.